On October 31st, 2020, Slovakia measured half of its population for coronavirus. 25,280 people were tested positive for coronavirus. Of that number, how many were false positives? People who were reported to have coronavirus who actually didn't. How many were false negatives? People who went home from that testing thinking that they don't have coronavirus, but they actually do. We're going to get into that into this lecture. And what we're really talking about is sensitivity and specificity and how those things play a role in testing, either coronavirus testing, psychological testing, or looking for terrorists or looking for difficult to find objects. And one of the things that I have noted is in a lot of articles, they talk about sensitivity and specificity, but they leave out one of the most important factors, the base rate of the problem. The smaller the problem is, the harder it is going to be defined. And the test will look worse in a smaller to find disease or problem. So let me start with just a Star Wars reference. I love this never tell me the odds type of reference. And what we're going to start with, and before we get into coronavirus testing and psychological testing, let's talk about how difficult it is to find a terrorist or find somebody who's going to cause mass problems. So thinking about airport security or other issues and what we're looking for a very hard to find object. So with security screening. Imagine we've devised a screening tool that can look at either it's an fMRI or some sort of screening tool, and we can find people who are going to cause an act of terrorism or mass murder. So this is a really an innovative tool. It's something that's really nice for us to find. The machine's quite good, 99% accurate. So we're going to find people who have this sort of issue. And let's analyze 1,000 people. And so we're 100,000 people. So as these 100,000 people go through the scanner, we're going to find people who are mass terrorists or have the inclination to cause problems. So in this example here, we've got this person in red that has this inclination. So out of 1,000 people, we'll label 10 false positives. So if it's 99% accurate, so we're 99%, so we're finding 10 people who we're claiming have inclination for mass terrorism. So these 10 false positives are there. So we find these 10 people and I'm switching numbers here, this is out of the 100,000. And so we find 1,001 potential shooters. So we found 1,000 false positive and one correct guess. And so with this problem, it's a very small problem. And so we have a very small base rate. So we find a lot of false positives out of 100,000 people. And even though it's a 99% accurate test, we're identifying 1% of the people incorrectly. And so that becomes a much bigger problem on scale. So with those, if we put all the potential mass shooters in red shirts, we find that one person is in the red shirt. We found that person correctly, but we also found a bunch of other people who aren't mass shooters. And this is kind of what goes on at the airport. You often get screened. I've been screened many times as I go through the airport, and you're indicated as a false positive. You don't really plan on causing a terrorist act. So if we look at school shootings and we think about this problem, this has been something that was bigger in the news before coronavirus, but it's a big issue to have these school shootings. It's very scary. It causes a big emotional response. There's been 2,271 mass shootings since Sandy Hook, and with at least 2,568 killed, 9,500 wounded. So quite a big deal is with these mass shootings. But if we put that on a chart, and this chart's a little bit difficult to see, and we look at the number of people killed in mass shootings by guns, that's that little row of red on the top, it's kind of a small number relative to all of the other people who have been killed by guns. So again, we're kind of looking at this emotional issue, and we talk about it quite a bit, or we did talk about it quite a bit, but it's kind of a smaller percentage as compared to gun deaths. And so if we break it down even further, we've got sort of the lighter red up in the top, and those are fatalities by murder with a weapon. And then the darker red boxes on the bottom are people who commit suicide. So we hear about murder much more than we hear about suicide, but suicide is the one that's most probable with a gun. So again, when we're trying to, this is kind of a little off topic, but just kind of thinking about the problems we're trying to find. If we're trying to find fatalities by guns, we're going to see a lot more people committing suicide, and I'm sorry, that's the incorrect term, dying by suicide than we will by being murdered or by mass shootings. But what we hear about in the news are kind of the other issues. We also don't hear about these other issues, and I'm a little bit off topic. I'm talking about more other issues, but heart disease, cancer, there are a lot of people dying from that, and that's a much bigger number than even suicide is, and we don't hear about that as much either. And that's something else to kind of think about the saliency of these issues. So I'm going to kind of move on to this topic and get back into the testing piece. So when we're talking about testing, we're going to be talking about sensitivity and specificity. So sensitivity is how well your test finds people who actually have the problem or have the disease. So we're finding people who are true positives. Specificity, on the other hand, is how well we're finding people who don't have the problem. So they're true negatives. So finding people who actually don't have the disease. So if we're really concerned about finding people, and that's our only concern, and we say everybody has that disease, we'd be 100% sensitive to that measure because we're saying everybody has it. We're not going to miss anybody who doesn't, but we'd be terrible at specificity. We wouldn't find anybody who doesn't have that disease. So we need to balance out these two. I worked at a neurology clinic, and the neurologist would refer people who were thought to have Alzheimer's disease to the neuropsychologist. We do the neuropsychology testing, and then we say, we think this person has probably has Alzheimer's disease or not. Most of the referrals from this neurology clinic were probably people who had Alzheimer's disease. So if we just wanted to be lazy and not do any testing, we could just say everybody has Alzheimer's disease, and we'd probably be right most of the time. However, if we took that same approach to general practice and we said everybody has Alzheimer's disease, we wouldn't be very specific at all. We wouldn't find people who don't have Alzheimer's disease. So that the main point of that, the base rate of the problem helps you find it or not, or kind of defines how well your test is, your sensitivity and specificity. And I'm going to go into the numbers behind this. So, and again, just now I'm going to just kind of bring it back to coronavirus testing and talk about those numbers and how come sometimes the coronavirus testing, we hear about inaccuracies, but then, and maybe what that's all about. So again, we have different types of tests. We've got the PCR test. This is thought to be, this is with the nasal swab. This is thought to be one of the best tests, the most accurate. We have antigen tests. These are more the rapid response tests. These are nice because they're more convenient. And then we have antibody tests, which are a completely different type of test, but they're looking for antibodies in the system. So we'll talk a little bit about those, but I'm not going to go into much detail about those. So this is from the Wall Street Journal. And this talked about early coronavirus testing. And the estimate of the sensitivity of this coronavirus testing was 70%. So meaning that 1 in 3 positive patients walk away with a reassuring negative result, but they actually have it. So they're, and this is actually getting at specificity in what this quote said, the first quote, but they were talking about sensitivity. And then another doctor that in this quoted in this article said a negative result is more likely to be accurate in places like Louisville, where prevalence is low, but virtually useless in New York, where it's high. What is that about? And they kind of didn't talk about that in this article, and kind of it's referring to the base rate issue that we were already talking about, but they didn't talk about it in this article. And it almost made it seem like these tests are just not very good in Louisville, but they're better in New York. And why would that be? And they just kind of left that open in this article. So one of the things I want to explain is why that's the case. And this was early on in the coronavirus when this article came out, and where New York was experiencing a surge of patients. They had a much higher base rate, and Louisville at the time was very low in those coronavirus patients. So just again, some other articles that I've seen, this was talking about just 1,070 specimens from 205 people, and they were looking at what's the most accurate. So all of the people in this, all 205 actually had coronavirus. And when they looked at the nasal swab, 93% said that they actually had coronavirus. So 93% were accurate. They had sensitivity. Looking at others just got lower and lower. So even things like looking at other types of blood, it wasn't very accurate. Looking at feces wasn't very accurate. So the nasal swab was the most accurate test. And this is with 100% base rate, they're finding 93% of the people. So again, this is an early study looking at PCR test early on in the process, and it was relatively accurate. But again, that missing 7%, we're not finding 7% of the people who actually have the coronavirus. And that could be very problematic, that if we're letting these 7% of people go home, and they could be infecting others. So again, in that Slovakia sample, they tried to sample on October 31st, 2020, 50% of their people, and they had 25,850 positive tests. And that's great. But what about, let's say it's 7% of people that they missed? They might have missed a large portion of people who actually have coronavirus that went home from the testing that actually have coronavirus and they're thinking that they're negative. And maybe they think they can be a little bit more active and take a little more risk because the test said that they're negative. So that negative, that not finding people, that lack of sensitivity could be very problematic. Again, some other examples, just the sensitivity in some of these early tests were not very good. So some of them were 96% in the laboratory where they knew the base rate was 100%. But in clinical settings, the sensitivity goes down to 66 to 80%. And this article talked about maybe it's, how the clinicians are swabbing and differences in the clinical setting. I actually think it's because of the base rate is the problem, is that you have a much lower base rate and you're testing a lot of people who actually don't have coronavirus. So your sensitivity is going to suffer because of that lower base rate. And then this is a new quick test from Abbott that came out. This is one that you can swab with saliva. And this had 97% sensitivity and 8.5% specificity. And they've got some rules about this. This is for people who are, I'm trying to remember the rules, asymptomatic or have been exposed to somebody. So there's a set of rules to get those numbers. So would this apply to the general population or not if we're doing testing? I'm not sure this would be the same numbers that we'd experience. So this looks like a really good test, but we're also going to have that same group of people who go home, they're false negatives. They're told that they don't have the coronavirus, but they actually do, and then they might be more risky and maybe infect others because they actually have the coronavirus and they've been told they don't. All right, so let me go into some of the details and the math behind this. And what we've got in this figure here is just, we've got the diagnostic state on top and whether it's present or absent. That's what's really the gold standard if we know that the person has it or they don't. And then when we can look on the column here to the left, we have the test result, whether it's positive or negative. So within that box, that TP is they actually have the disease and the test says that they have the disease. So that's a true positive. The TP stands for true positive. So that's that getting at that sensitivity piece to true positive. We want that number to be really high. Moving across that row, the test says that they're positive, but they actually don't have it. That's a false positive. So that's somebody telling somebody they have coronavirus, but they actually don't have it. So that's a false positive. So if we take the true positives, the number of people it actually found, add it to the false positives, we get this total here, and that gets at sensitivity. So if we divide, so sensitivity, the formula is down below. We take the true positives, divide it by the total, we get our percentage, and that's the sensitivity percentage. So how many people did we find, how many people did the test find that actually have the coronavirus? So if we found, let's say out of 100 people, we found 99 people that have it, that actually do have it, but the test found one person who's we said had it, but they actually didn't have it, we'd have a 99% sensitivity. The second row gets at specificity, and we've got kind of that same thing. I'm going to go to this TN part of the figure. That's true negatives. That's people who actually don't have the disease, and the test says that they don't have the disease. We want that number to be as high as possible. And then we also have false negatives, people who have the disease, who actually the test says that they don't have the disease. So they actually have the disease, the test says that they don't. So we want that number to be really small. And then we do that same sort of formula for, we take the number of true negatives, divide it by the total, and that gives us our percentage of our specificity. So that gets at our sensitivity and specificity. So again, we want to find those people who actually have it, and we want to find the people who don't actually have it. We want to eliminate the false positives and the false negatives. And in the coronavirus case, we probably are more concerned about false negatives because they could be have more risky behaviors. I guess we're also worried about false positives because we're isolating a person who actually doesn't have it. I think Nick Saban, the Alabama football coach, tested positive, and he said he was asymptomatic. The next test wasn't positive. He thought he might have had a false positive, and that might have prevented him from coaching and practices and doing things. So maybe a false positive would have been really bad in that situation too, especially if you're an Alabama football fan. But we can imagine other situations where a person is isolated with a false positive, and that could be damaging to their career, family, other things. So, but false negatives in my mind are going to be more damaging because that person could be infecting more people. All right, so I'm going to get into now how the prevalence rate or the base rate affects the diagnosis and our sensitivity and specificity. So let's say we've got on the left, we've got a 5% prevalence rate. And on the right, we have a 25% prevalence rate. So if we look at these numbers, we've got all the reds are where the test is correct in the positive. So the red dots, they have a correct positive test that says that they're positive. All the ones in the red with the grayed out X are the ones that are false negatives. So we can get at our sensitivity with this top line here. So this we can see one false negative and a bunch of true positives. So that's our sensitivity. Our specificity are with the gray circles. So the gray circles that are all by themselves gray, they've tested negative, and they actually don't have the coronavirus. So these are the gray circles. And again, we have a 5% prevalence rate. So most everybody doesn't have coronavirus in this situation. However, when there's an X in there, that's where they've had a, I actually messed this up. This is false positives. These are where the red X, the test says the person's negative, but they actually have the coronavirus. So we're finding, or we're saying that a lot more people have the coronavirus than they actually, this group of people don't have the coronavirus. So when we have a small base rate, we're finding a lot more false positives, a lot more people. It's harder to find. And this is the same thing we saw with the earlier example where we had the terrorist. It's hard to find, and we're going to get a lot of false positives. So when you go to the airport, you're getting pulled off to the side to get extra screening. Those are all false positives. Because the base rate is so low, there's a lot more false positives that are coming out. On the graph on the right, we have a much higher prevalence. It's an easier problem to find. So we have fewer false positives. We're finding a bunch more people that actually have the disease, but now we're starting to get more false negatives. So we're getting the people that, again, when we're getting people who don't have the disease, or who have the disease, but the test says they don't have it. So this group of people up here, this is the people that could infect others. So the risky people, they might be taking more risk because they've been told their test is negative. I'm going to break this down in a little bit more in this slide here. So again, this is our 5% prevalence rate. That was the graph on the left. It's up here in the right quadrant. And we've got my Excel spreadsheet here. This test has got a 95% sensitivity, 95% specificity. So it's a pretty good test. But when we look at it, we've got a lot of false positives. And in this situation, we don't really have any false negatives. It's a rounding type of issue here where it's kind of rounded this. We actually have, it was a percentage of a person in this Excel spreadsheet, but in here we have just one false negative. It's probably a point something is this number. So here, again, we're pretty good at finding the people who don't have it because the base rate's really low. Most everybody doesn't have it. So when we have only 5% of the people who have it, we can really find those people who don't have it. But we're not very good at finding the people having it because we have a lot more false positives. So because it's such a small problem, we can't find, we're going to give a lot more false positives in that situation. All right, and I'm going to just kind of reiterate this point with this 25% prevalence. And so we're have a lot more people to find. So we have fewer false positives because we're better at finding the people who have it, but now we're getting more false negatives. And so this is that false negatives in that top left of with those gray X's in the red circles. And so these false negatives, if we look at the situation and moving over to the chart on the right, when we have at the bottom of that chart, all the red circles. So if you tested positive, you have an 86% chance of actually being positive because there's a lot of false positives in this situation. And if you tested negative, all the gray circles on the top, you've got a 98.3% chance of actually being negative. So again, the base rate, going back to this slide, changes how many false positives, how many false negatives there are. So when we're measuring anything, and when we're looking at a laboratory situation where they're testing these things, they're testing it on a population of 100% of people who have coronavirus. So when we put it out in the clinic, it changes the numbers because of the base rate. And depending where you're at, your test is going to be making more false positives or false negatives because of the. So to summarize, the base rate plays a big role in how well our test looks like it's doing. So if we have a really small base rate, a very small problem when we're trying to find it, our specificity is going to be much better because we can find people who don't have it much easier because they're easier to find. We can just look around and there's a lot more people who don't have it. If the base rate is really high, our sensitivity gets better because it's much easier to find the people who have the disease. So again, the example I gave earlier was in the neurology clinic. We were very sensitive at finding people with Alzheimer's disease because most everybody we saw had Alzheimer's disease. So it was an easy situation for us to be very sensitive in our testing. Again, this is an issue that I don't think the media is covering very well. They talk about the sensitivity and specificity of the test. And when you see a number like 95%, it makes it seem like a really good test. But then again, when you're testing millions of people, you need to know the base rate to find out how many false positives you have, how many false negatives you have, and whether you're going to send people home thinking that they don't have it who actually do have it, or you send people home thinking that they have it when they actually don't have it. So those false issues can make a bigger problem on a larger scale, even though we have a very accurate test. Because we're testing people on a large scale, those false negatives and false positives become more problematic.